Central Time. I apologize. Hopefully you guys can hear and see me. I made some attempts to actually start the stream at 12 o'clock, and for some good reason, my computer just wasn't allowing me to do it. All right, so let me verify that I'm streaming. And so I really had to like reset a lot of stuff to hopefully fix the problem. Um, so right now I'm reaching out. Okay, I got a verification that I can be seen and heard right now. All right. So I apologize for the black background, guys. I had to reset a lot of stuff from my OBS software. But the overall plan for today is to step away from the research I'm currently doing and just talk about something that's a little bit more different. Um, whoa. Am I still, can you guys still see and hear me? I'm just going to go under the assumption that you can. My computer just did something really, really weird as far as the stream is concerned. Okay. All right. So what we're going to be talking about today are two of the fundamental forces. Those being the electrostatic force, which of course is linked to magnetic force, and the gravitational force. But again, before I do that, let me first verify that I'm actually streaming, because my OBS software says I'm streaming, but I'm now logged onto Twitch and I'm not seeing anything. So let me go ahead and start at least setting up some of the windows I'll need to discuss this today. Okay, thank you, Gordon. All right. So I am streaming. I'm just gonna go off of that and just continue, even though I can't currently see everyone's chat. All right. So I'm going to need my text editor to do this. So let me go ahead and pull that up and add that. Perfect. And so let's go ahead and let's do latex template. And so I guess I'm going to entitle this, which is more powerful, the gravitational force or the electrostatic force. So which is greater? Electrostatic force or gravitational force? All right. Let's go ahead and typeset this. I'm just going to save everything to my desktop. I'm not going to worry about setting anything else up. And you guys cannot currently see the output, so let me go ahead and make that also available to view. So PDF. And where are we at? This is what I want. All right. Let's go ahead and make some quick modifications to the screen. And guys, again, I apologize for the technical difficulties. I have no idea what was going on. I wouldn't be shocked if one of my kids got to my computer and did something. Let's make some of this text even bigger. All right. I think this should be good. All right. And I'm gonna. We don't need this one actually. We'll take this away. So no need for an author for this. All right. No need for an author for this because the answer for this is already known. But so let me ask you guys, which force do you think is greater, the electrostatic force or the gravitational force? Let me try my best to see if I can. Okay, am I cold? No, Peter, I'm not cold. It's actually a good temperature inside the house right now. I'm wearing. You guys can't see it, probably, or hopefully you can see it, but I'm wearing my CosmoQuest hoodie. What? I want to be able to see the comments. Come on, Twitch, work with me. This is just so upsetting right now. First, I had issues with my OBS software. Now I'm having issues with Twitch. Come on. All right. Again, guys, I cannot see your comments right now, unfortunately. But I'm just going to keep going with what I got here. And so, as I was just stating, we want to know exactly which one is greater. And really, it depends on the scale at which you're looking at, right? And what I mean by that is, depending on the particular situation that you're talking about. If you're talking about simply two masses that are neutral, that is neutrally charged, then of course the gravitational force will always be the greatest between the two um, particles. However, whenever you have particles that are charged or have some sort of net charge to them, then you might have to consider this. When you put these two particles within some proximity to one another, which one of these forces will dominate? And the overall question is, it heavily depends on not even scale, actually, now that I think about it. And I'll prove this in just a second. But the situation should always be that it depends on the mass to charge ratio. And so let's go ahead and work through this problem to determine which one of these two forces is greater. So I'm going to go ahead and give the two equations. So I'm looking at Twitch, well, not Twitch, at Slack. And right now, this is the only way I can communicate with you guys is if you have access to the weekly Space Hangout Cruise Slack um, channel. And so I have Larry saying gravity for the long range. um, but in a few seconds, we're going to quickly see that scale is really not that important with this particular problem. All right. So let me pull up my tech window, and we're going to go ahead and type out what the equation is for gravitational force. So no indent, gravitational force equation. Begin, align, end align. I should make sure that I'm using all the proper packages for this to work properly. So we're going to go ahead and use package. And if I'm not mistaken, I think it's AMS math. Sometimes whenever I have to remember something, I have to look up. It's up there. The information's up there somewhere. And I got to go looking for it. All right. And so just to make sure that this is working, let me go ahead and typeset it. See if I get any errors. It looks like I didn't get any errors. We're good to go. All right. I'm going to go back to Chrome, Twitch. Come on, work with me. I want to be able to see comments. All right. We're just going to keep going, guys. And again, this is a really bad day for me, technologically speaking. My software is failing me right now. All right. So the gravitational force equation is F equals, and it's going to be a fraction, capital G, a capital M, I'll put a subscript 1 for this, which corresponds to the mass of one object. Or let's put A, actually. The mass of object A and the mass times the mass of object B, all divided by the physical distance, which I'm going to be representing as R, that quantity, or that distance squared. And so this represents the magnitude, scroll down, this represents the magnitude, the gravitational force magnitude between two masses. Basically stating that whatever your mass may be, whatever the physical magnitude of your mass may be, those two masses will gravitationally attract one another. So, as a human walks by another human on the street, those humans are gravitationally attracted to one another. Which was pretty cool when I first found this out. My thoughts on gravity were that, well, going into astronomy, my thoughts on gravity were that, oh, only planets and stars, really, really massive objects gravitationally influence other objects. Like satellites, the moons that orbit the planets. The reason why people don't just float off into space is because we're gravitationally attracted to Earth. But this equation basically shows that every mass is gravitationally attracted to every other mass, no matter what distance they are away from one another. It's just that some masses have a bigger gravitational influence than others. All right. So let's go ahead and move on now to electrostatic force. Interestingly enough, it has a very similar equation as the gravitational force. So let's go ahead and we're going to put electrostatic force or Coulomb's force. So electrostatic force. Or better yet, let's put Coulomb's, electrostatic force. Coulomb's law. Or Coulomb's force. Equation. And so what we're going to get for this, let's see if Twitch wants to work with me so that I can see everyone's comments. Yeah, guys, for now, electrostatic rules in plasmas. Very much so, that's correct. Thanks, Guido. So I'm gonna go ahead over to the CQX Streams channel, and whatever questions that you guys have to say here is where I'm just basically gonna be looking for. So Susie says the electrostatic is stronger. Well, we will see. We will see. All right. So far I've heard that gravity works. I believe someone said at long ranges, and Susie just stated the electrostatic is stronger. It's outright stronger. All right. So let's continue with this problem for today. So the electrostatic force equation, like I said before, is very similar to the gravitational force equation, except now we have a new constant which I'll just name as k. And instead of the masses of two objects, we're looking at their charge, the magnitude of their charge. So the charge of object A times the charge of object B times the electrostatic force equation constant K, all divided by the physical distance r between them, that quantity being squared. So I should basically denote that these two equations are different, right? So the very first equation should be F sub g, where the capital G corresponds to gravitational force. And then this should be F sub E, where this would correspond to the electrostatic force. Perfect. All right. So we want to be able to compare these two things, right? So what's the best way to compare these two forces? What do you guys think? How should we go about comparing them? All right, let me pull up my Slack. Oh, no wrong, no, don't worry, Susie. No worries, Susie. Actually, when I was first asked this question, or when I first asked myself this question, it was actually in graduate school, and I did not know the answer. And I did this little exercise to find out that certain things you don't have to worry about. But what do you guys think? How should we go about determining which of these forces is greater? All right, so I'm going to go ahead and actually answer that because I wanted this to be a little bit more interactive, but then again, I can't see the chat. And I don't know why. Even though I really want to be able to see the Sorry, I was reading Larry's comment about dry ice. Yeah, from my understanding, if I'm not mistaken, dry ice is isn't dry ice just is it carbon dioxide? It's solid. Isn't it solid carbon dioxide? The M's and Q's have to be equal. Ooh. So Larry is talking about the fact that if the product of the masses is equal to the product of the charges, then the forces should be equal. Let's see. So thanks truck Captain Stumpy. So it is so dry ice is frozen carbon dioxide. And yes, definitely agree with you that it sublimes. But there might be a condition where it can actually be a liquid though. I would have to look at the I think it's a pressure versus volume diagram to determine that. So Guido says he has no idea. But it is a trick question. You're right. So let's go ahead and the way in which we can compare these two forces is we divide them. We take the ratio. So to compare forces, take ratio. To compare forces, take ratio. In fact, to make any sort of comparison between two equations, taking the ratio is typically the best way to go. All right, so I'm going to be doing a lot of copying and pasting here. And let's just go ahead and do the electrostatic force divided by the gravitational force. And so in doing that, we get the following. All right, so fraction, this is going to be my upper fraction, and then my lower fraction is just basically going to be the gravitational force equation. And let's go ahead and typeset that. All right, so this is where we're at. All right, perfect. And let's make that bigger actually, because that's kind of hard for, it looks like it's hard to see. All right, so now note, between these two equations, the thing that's the same is the variable r, right? The physical distance between the two objects, that distance r is the same. So as we already see, the length between the two objects drops out, it divides out. So the to be able to compare these, or to determine which one is has a greater force than the other, it's completely independent of scale. It's completely independent of the distance between the two objects. So let's go ahead and modify our equation to take this into consideration. So we should now basically just get KQA times QB divided by GMA times MB. All right, there we go. That's a little bit better. You guys can see what I'm typing too. I am going to take this one and take this one. And hopefully this gives me exactly what I want. All right. And so earlier I was stating that it's dependent upon the charge mass ratio. But this is where we can test a few conditions actually. So Larry hinted at, hey, if the magnitude of the product of the charges is equal to the magnitude of the product of the masses, that is, under the condition that QA times QB is equal to MA times MB, that means that their ratio must equal 1 in that condition. So we're going to consider that condition. And so this is basically how you evaluate an equation. You do like in the limit of this. So this is in the limit as the product of QA times QB is equal to. So let's actually write that out. We're doing a limit right now. So how would I write this out? It's been a while since I've used tech. So consider the condition where, let's go into math mode, is equal to this. So Q sub A times Q sub B is equal to M sub A times M sub B. Let's see if I'm missing any comments here. Liquid CO2 is used in decaffeinated coffee. So it appears that both Larry and I do not like coffee. Well, in this case, decaffeinated coffee, but I don't like coffee, period. All right. So we're considering the condition where the product of the charges is equal to the product of the masses. And so to write that out, we'd have to write a limit. What did I just do? There we go. Pressing the wrong buttons on my keyboard there. So I'm going to rewrite this as I think it's just limit. Lim. And I think I can put underscore. And the limit as QA is equal to, or the limit as QA goes to, or the product of the charges goes to the product of the masses. I can't remember exactly how to do this, but hopefully this will pass. Okay. That looks okay. All right, let's see what it looks like. There is a lot better way of doing this, but this is how I'm going to do it for right now. Let's make it a little bit smaller. That is, the formatting is kind of off, but this should work. So basically, as the product of the charges goes to become equal to the product of the masses, we get something very simple, actually. We end up getting that limit should basically just be the ratio of the constants, K over G. And so now we're actually getting to the part where we can actually determine, well, which force is greater than the other one. And so to determine this, we need to know exactly, well, what are the physical values, what are the magnitudes of K over G. And so what I'm going to do is I'm going to pull up another scene that will allow me to have an internet browser open. That way we can all see it together. So what are the units for M's and Q's? How are they reconciled? This is Larry's question. So if you're in SI units, the units for the mass would be kilograms, and the unit for charge would be the coulomb. And they're reconciled by the r squared in the denominator and the constants themselves. The constants have units as well. The constant K has units and the constant G has units. And ultimately what you'll end up getting is the Newton for both of them. That is, the Newton is the unit of force. All right. I want to pull up a web browser. So let's go ahead and create another scene. Better yet, sorry about that. Let's duplicate my current scene. it didn't like that. Okay. I'm going to get rid of that scene. And I'm going to go ahead and I was not aware that this entire time I had black space right there. Okay. Let's go ahead and just get rid of these windows because they're not needed for this particular scene. This is what happens when you have technical difficulties like I had. I have to reset a lot of stuff, and it's taking time to do so. Alright, let's go ahead and use Safari for this. Window capture. This is Safari. And so I do have one thing to say, and that is that G is actually a constant, right? It's the gravitational constant is always simply just going to be G. However, K actually breaks down into other more fundamental constants, which we'll see in just a second. Let's go ahead and start with the gravitational constant first. So, right, here we go. So note, we've already made the assumption that the product of the charges is equal to the product of the masses. So gravitational constant. And the only thing that will determine now which force is greater than the other is the ratio between K and G. And so what we get here is that the gravitational constant has this value. And from now I'm just going to copy and paste. We're not even going to worry about the units. Well, I'll keep the units too, actually. Even though the units in this case is not the important thing. We're worried strictly about the magnitudes of the two forces. All right. Back to tech. I'm going to go ahead and start substituting some stuff in here. Okay, so this is a fraction. And the bottom should be this. And so 6.6, that's not going to work. Let's just put times. This is 10 raised to the negative 11, which is the key information I really want here. M raised to the third power. The kilograms raised to the negative 1 power. And the time unit, which is in units of seconds, raised to the negative 2 power. Let's see what this looks like. Hopefully it's... Well, let's first format it correctly. And now let's see what it looks like. All right, so far so good. So just note, guys, that in all honesty, we don't really need the units, right? Because the units should cancel out. Because if you look at the left-hand side of the equation, we're basically dividing units of newtons by units of newtons. So we don't even have to worry about the units. I'm going to get rid of the units so we can look strictly at magnitude. So our force constant, the gravitational constant that is on the order of roughly 10 to the negative 11. Let's go ahead now and find out OBS. All right, let's first allow you guys to see what I'm talking about here. All right. So basically what I was saying a few seconds ago is that the left-hand side of the equation shows the units should cancel out because the unit for force, independent of whether you're talking about gravitational force or electrostatic force, the unit is newtons. And basically, since you have newtons in the numerator and you have newtons in the denominator, it cancels out. So far on the right-hand side of the equation, I've already put in the magnitude of the gravitational force constant. And we can see it's on the order of 10 to the negative 11. The next step, of course, is to now figure out Well, what is the magnitude of our electrostatic force constant, K?